Okay, I'm Milton Mendonça. I'm from the Department of Ecology in the Federal University of Rio Grande do Sul, which is the southernmost state in Brazil. I'm an ecologist by nature. I'm bringing you here about ecosystem engineered species effects as potentially ambiguous technosignatures. Thank you very much for having me. Let's say my theoretical basis is from ecology, but I like astrobiology a lot, and I think there's lots to share between these two disciplines. We had a paper in 2024 about how this transdisciplinary astrobiology needs to be inclusive of ecology as well. Ecology has been kind of overlooked in astrobiology, much because of ecologists not taking enough interest, I guess. But there are conceptual opportunities as well as experimental and observational ones. So that's why I'm here. What I'm trying to argue about technosignatures here is that we need technological analogs, which means astrobiology works from analogy from different ways. We have actually a paper coming up speaking of how much we need a specific targets when we use analogy, and specifying similarity degrees, that is how similar things between the comparisons we are making. So what would actually be an adequate technological analog for in general? Are humans really the only option we have? Well, we think so, so far, but I would like to turn the question around, because we have different kinds of analogs from other organisms in our Earth. So other organisms produce tools and produce different forms of architecture as well, not usually machines or codes, which are the other forms of technology. We can see apes and mammals in general, other vertebrates such as birds and fish, employing tools in different fashion, building structures in different fashion. Cephalopods do it, arthropods do it, insects and arachnids. Actually, all organisms produce some kind of direct physical influence on the environment. We call them ecological effects, exactly. What we have is that humans apparently have specific ecological effects different from the others. But how different would they be is actually my question. So I'm introducing this concept of ecosystem engineers. I don't know if you heard about it. It's proposed in the 90s. Because we recognize that there are species that create and or strongly change the habitats they inhabit due to their structure or their actions. Even though these modifications can be localized, it changes environmental conditions, it modulates the resources, which means it creates new resources, or it changes how the resources are available for other species, for both the species causing this engineering and for other species in the environment. So it allows the occurrence of other species. It increases species richness for different environments as well. You have some examples here, like trees and kelp and termites producing huge mounds, and earthworms producing tunnels in the soil, helping aerate and helping access to water. And the quintessential ecosystem engineer, which is beavers, which produce dams, who change an ecosystem of flowing water to an ecosystem of still water, changing completely the fauna that is able to exist in this environment. So all of the organisms, as I said, are somehow ecosystem engineers. We change the environment we are, but some have a disproportional effect. So that we also call them keystone species. So they are key to the environment, and they change the environment, the physical and chemical environment, in a way that is really important. There are two different ways to be an ecosystem engineer. The first one is being autogenic, which means it creates a habitat just because of its body structures, just because of the way it is, which happens for trees, for kelp, for corals, for moss, by creating peatlands, for example. But there's another way to be an ecosystem engineer, which is being allogenic, which means it's usually animals that mechanically change living or non-living materials and then change the habitat for the other species as well. And all the other examples I use, earthworms, termites, and beavers, all are allogenic environmental engineers. So just to detail a bit more about what these ecosystem engineers are, what they are, how they change the environment. Some of them can be social. Actually, most of the groups that produce sensible, important changes in the environment, like apes, bees, wasps, ants, and termites, are actually collaborative, are social, which helps a lot, of course, with many individuals collaborating to produce a huge impact in the environment. But not all of them could need to be social or even intelligent. Some ecosystem engineers are only moderately intelligent, which means they are able to solve complex problems, but usually in a social way, because they can adapt to environmental changes, but they're not really using higher forms of intelligence, let's say. So it's not really what we would call technology. And the effects in the ecosystems, of course, are sometimes very large. We have these huge termite or ant mounds across different environments, like savannas here. Most of the effects of the allogenic ecosystem engineers come from building, from nests and holes. It's innate behavior to respond to environmental heterogeneity, which means it can appear different from different habitats. But some are spatially repeated, like this termite mounds I'm showing you here on the left. And some are even coalescent, like beaver dams, which you see up in this photograph, this aerial photograph in the upper right, which is a beaver dam with 150 meters. So some of these structures can get really large, and some of the structures can even be seen from space. So here we have 4 different situations where ecosystem engineers have created structures that can be seen from space. On the left, on the upper side, you see the Great Barrier Reef, which is produced by lots of different species of coral. On the upper right, you see the Amazon, which is a forest produced by lots of species of trees. On the lower left, you see, again, the termite mounds, which are repeated, which can be confounded with different engineered instructions from space. And on the lower right, you see an example from humans, which are, of course, ecosystem engineers as well, in the form of night lights. So my question is, are these ecosystem engineers producing signatures that we would interpret as biosignatures or technosignatures? If we never even knew what a coral is or how a coral reef is built, would we recognize the Great Barrier Reef from space as a biosignature, as a technosignature, or even not as a biosignature, as some natural geoformation, for example? So I think we need to stop and ponder about scenarios for why would ecosystem engineers appear evolutionary? Do they provide analogs for specific biosignatures? How distinct these biosignatures would be from technosignatures? And my point is exactly that. I think these guys are actually defining the limit between these two concepts of biosignature and technosignature. So is an agnostic technosignature even possible? Technology like large planetary physical structures might be confounded. We could expect to find in other biosphere giant scale ecosystem engineers who could produce certain physical structures we could think they are technosignatures, but they would not be. And the same for chemistry. On the left, you see the rather small termite mounds of the Earth, but we could think of really large termite mounds on other planets, especially smaller planets where gravity would be lower, for example. And on the left, you see pictures of how beaver dams change the chemistry of the river, which we can see because of the color of the river. And on the right, of course, how we produce our dams, and that also changes the planetary chemistry and, of course, all the dynamics of the river system. So to paraphrase Smith and Matthews, technology detection is living in a universe of false positives. Just to bring you one final rather complex scenario, we have some of these termite mounds in Brazil, large termite mounds, which are occupied by another species, by a species of beetle, for which the larvae use bioluminescence to prey. So they produce this light, you can see, this greenish light you can see there, to attract insects that they eat. So in a different setting, in a different biosphere, where we can have these large structures, like spatially arranged in the environment and producing bioluminescence, would we take this for city lights? So in other biosphere, perhaps some of these allogenic environmental engineers could produce effects that are bordering on the technological, and that would be globally important in different settings. So, ecosystem engineer false technosignatures, we have lots of questions about that still. Is this only relevant for future missions with direct exoplanet imaging in very fine detail? Perhaps, but I think it's helpful, at least conceptually, to take a look at these questions. Which kind of theoretical perspective for studying this spatial organization of technosignatures would we need? We could use, for example, information theory or graph or network theory or geometric or fractals to distinguish between these, between proper technosignatures and perhaps these specific biosignatures for environmental ecosystem engineers, sorry. Which variables could we use? We could derive this from the landscape ecology, from our urban studies as well. So I think we need to consider this alternative hypothesis. Technosignatures, complex structures need not involve necessarily intelligence. And ecosystem engineers are only one possible case. Perhaps nature has much more to bring. So these are the references I use, and I leave you here. Thank you very much.